We ended the last video with the question of how do we classify critical points. And so the answer, it turns out, is what's called the first derivative test. And so the setup is, let's let C be a critical point of our function, and then the following statements are true. So one, if f prime, if the derivative changes from being positive on the left to being negative on the right at x equals c, then f has a local max at x equals c. If the derivative changes from being negative on the left to positive on the right at x equals c, then f has a local min at x equals c. And if f does not change sign at x equals c, then f has no local extrema at x equals c. Let me show you just real quick a little picture that I keep in my head that I think helps me remember this, and I think it'll help you too. Okay, f prime is telling me the slope of the tangent line. So if I'm positive on the left, I have my function has positive slope on the left. If I'm negative on the right, I have negative slope on the right. And what's that? Oh, wow, that's a local max. Similarly, if I have negative slope on this side and positive slope on that side, then I have a local min. And if I'm not changing sign, maybe I'm positive, 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 and positive, well, I don't get a local max or a local min. I don't usually draw that one, but I did this time. Okay, so let's go back and redo our previous example. So we wrote down this particular function, we took its derivative, we factored it, we came up with this number line for f prime. All of this is in one of the previous videos. And so the point is, with the increasing decreasing test, you can see that f is increasing from 3 to infinity and minus infinity to minus 1, and it's decreasing from minus 1 to 3. But the same work that you did for the increasing decreasing test also tells you a lot about local extrema. And so I'm actually going to use my pictures here to help me see it. Look, f prime is positive on this side of minus 1, and it's negative on that side. And then it's negative on this side of 3, and it's positive on that side of 3. So the same computation actually tells me that, I'll say thus, f has a local max at x equals negative 1 and a local min at x equals 3. Now, if I want to say what the local max is, I didn't say that, then I would say I could add of f of negative 1 equals, and then whatever you get when you plug in negative 1. Let's do it. So negative 1 minus 3 plus 9 plus 4, 13 minus 3 is 10. It looks like it's 9, right? F of minus 1 is 9. Hopefully I did that correctly. So if you want to, you can actually say what the local maximum value is. That's going to be very useful when we're graphing these. But the big thing is that you can just locate them. There's a local max here, there's a local min there, and then you can always plug the point into the function. One more example to illustrate this. We had f of x equals x cubed as a counterexample to the converse of Fermat's theorem. Let's actually use the first derivative test to see why there's no extrema there. We could see it graphically before. F prime is 3x squared. And so we're going to make a number line for f prime. F prime is only 0 when x is 0. Plug in 1, you're positive. Plug in negative 1, you're positive. F prime is not changing sign at 0. So we can actually conclude now that f has no local extrema at x equals 0. So I'll stop this video here. In the next video, we're going to begin to explore what the second derivative